A-level mechanics, kinematics, distance and velocity graphs. Let's start by looking at distance time graphs. Now in the example below, the following graph represents the displacement of a motorist from his home. The first thing we notice is the time is placed along the horizontal or x-axis and the distance is placed up the vertical or y-axis. Now in part 1 we're asked what is his speed from A to B. Now if we look at the distance of going from A to B, A is at a distance of 0 from his home and B is at a distance of 20 kilometers from his home. So that means going from A to B is 20 kilometers, and if we look along the horizontal axis we see that's in half an hour. The speed is the distance divided by the time, which is 20 divided by a half, which turns out to be 40 kilometers per hour. Now we notice the gradient of the line AB is also 20 over a half. It's the height over the base of the triangle and also works out to be 40. Now in part 2 we're asked to find the speed going from B to C. Well, B is a distance of 20 kilometers and C is a distance of 50 kilometers. So that's a distance of 30 kilometers. And the time is from half an hour to 2 hours, so that's an hour and a half. So, going from B to C, the speed is 30 over 1.5, which is 20. So the speed is 20 kilometers per hour. But we can also notice the gradient of the line is the height of the triangle over the base of the triangle, which is also 30 over 1.5, which is 20. Now in part 3, we're asked, what's his speed from C to D? Well, he doesn't move at all. His distance remains constant, and so his speed is 0. But also the gradient of the line is 0. And in part 4, we're asked, what's his speed from D to E? Now the speed is the distance travelled, which is 50 kilometres, over the time taken, which is 2 hours. So it's 50 over 2, or 25 kilometres per hour. But the gradient of the line DE is minus 50 over 2. The line has a negative gradient, which is minus 25. Now in the previous cases the gradient was equal to the speed. Here the sign has changed. The gradient is equal to minus the speed. Here's where we encounter the idea of velocity. Speed is always a positive number. With vectors, we must decide which direction is forward, then when moving forward, the velocity is equal to the speed, and when moving back, the velocity is equal to minus the speed. So the velocity from D to E is minus 25 kilometers per hour. So we have the following result. On a displacement time graph, the gradient of the graph at any point represents the velocity of the object. Let's have a look at another example, example 2. A motorist drives from London to Brighton, a distance of 80 kilometres. He leaves London at 9 o'clock and for the first 45 minutes he travels at 20 kilometres per hour. For the next half hour he drives at 80 kilometres per hour before stopping for half an hour. He then continues to Brighton, arriving at 12 o'clock. He stays in Brighton for half an hour and then returns to London at a constant speed, arriving back at 1400 hours. In part 1, draw a distance time graph for his journey. Well, the first thing we do is we draw a graph. Along the horizontal axis, we put the time, which starts at 9 and finishes at 1400 hours. And on the vertical axis, we draw the distance, which starts at 0 and goes up to 80 kilometres. Well, if he leaves London at 9 and drives for 3/4 of an hour at 20 kilometres per hour, he will have driven 15 kilometres. So we draw a line starting at 9 o'clock and a distance 0, going to 9:45 at a distance 15. It then says for the next half hour he drives at 80 kilometres per hour. That means in half an hour he will cover 40 kilometres. So we draw a line going across half an hour and going up 40 kilometres. He then stops for half an hour, so that means on the graph we draw a line horizontally across for half an hour. And then finally he arrives in Brighton at 12 o'clock, so we draw a line going across to 12 and up to 80. He then stays in Brighton for half an hour, so we draw a horizontal line for half an hour. He then comes back to London at a constant speed, so we draw a line arriving back in London at 1400 hours. In part 2 we're asked, what is his speed as he approaches Brighton? Well, if we look at the section of the graph as he approaches Brighton and draw a triangle underneath, we see that the height of the triangle is 25 kilometres and the base of the triangle is 1¼ hours. So his speed is 25 over 1¼ or over 1.25, which is 20 kilometres per hour. In part 3, it says, what is his speed on the journey back? Well, if we look at the graph, we see that it takes him 1½ hours to get back to London, and the distance travelled is 80 kilometres. So his speed is 80 divided by 1.5, which is 53½ kilometres per hour. Now the question goes on. A second car leaves Brighton at 10:30 and travels at a constant speed to London, arriving at 1300 hours. It then asks, from the graph, find the time at which they pass each other and their distance then from London. Well, for this graph we draw a straight line starting in Brighton at 10:30 and arriving in London at 1300 hours. We can then see from the graph that they pass each other at about 61.5 kilometres from London at about 11:05. Now let's have a look at velocity time graphs. We have the result. On a distance time graph, the gradient of the graph at any point represents the velocity of the object. So if we know calculus, we can say v equals ds by dt, which means that s is equal to the integral of v dt. This states that on a velocity time graph, we have the area under the graph is the distance covered. Now we can see this on a simple graph with constant velocity. Now we know in general distance is equal to velocity times time. And in the graph, the area of the rectangle is also the width times the length, which is the velocity times the time. So the area under the graph represents the distance travelled. Now let's consider acceleration. Acceleration is a measure of how fast an object speeds up. In motoring terms, acceleration is measured as something like 0 to 60 miles an hour in 6 seconds. This means the car can reach 60 miles per hour from rest in 6 seconds. 0 to 60 miles per hour in 4 seconds would be a greater acceleration. So acceleration is the rate at which the velocity increases. On a velocity time graph, the acceleration is the gradient of the graph. Since acceleration is the rate the velocity changes per second, the units are change in meters per second per second. That is, meters divided by seconds, or meters divided by seconds squared, or ms to the minus 2. If an object is slowing down while travelling in the positive direction, or accelerating in the negative direction, it has negative acceleration. When slowing down, it's called deceleration. Remember, on a velocity time graph, we have the acceleration is equal to the gradient of the graph, and the distance covered is equal to the area under the graph. Let's look at how we can use those results to solve a problem. In the example, below we have a velocity time graph for a particle. Find the acceleration and distance covered for each section of the graph. Well, to solve this, in section AB, the velocity increases from 0 to 10 in 2 seconds. So, the velocity is increasing by 5 meters per second each second. So its acceleration is 5 meters per second squared. Now we could just look at the line AB. Under it we have a triangle with a height of 10 and a base of 2. So the gradient is 10 over 2, which is 5. So again, the acceleration is 5 meters per second squared. Now the distance covered is the area under AB. So it's a half times the base times the height, which is a half times 2 times 10, which is 10 meters. In part B, if we draw a triangle under BC, we've got a height of 14 and base of 1, so the gradient is 14 over 1, so the acceleration is 14 meters per second squared. Now the distance covered is the area under BC. Now this is a trapezium, so the area is a half times the top plus the base times the height. Now the trapezium is on its side, so the top is 10 and the base is 24, the height is 1. So the area is a half into 10 plus 24 times 1, which is 17 meters. So the distance covered is 17 meters. Now in section CD the velocity does not change, so the acceleration is 0. The gradient of the line CD is also 0. The distance covered is simply the area of the rectangle under CD. So that's the width times the height. Now the width is 1.5 and the height is 24. So that's 1.5 times 24, which is equal to 36 meters. So the distance covered is 36 meters. In section DE, the particle is decelerating from 24 meters per second to 0 meters per second in 1.5 seconds. So the gradient is minus 24 over 1.5, which is minus 16. So we can say the acceleration is minus 16 meters per second squared, or the deceleration is 16 meters per second squared. Now the distance covered is the area under DE. This is a triangle, so it's a half times the base times the height, a half times 1.5 times 24, which is equal to 18. So the distance covered is 18 meters. So the total distance covered is 10 plus 17 plus 36 plus 18, which is 81 meters. Let's look at another example. A car at rest at a set of lights moves away with a constant acceleration when the lights change. Once it reaches a speed of 16 meters per second, it continues with a constant speed for 25 seconds. It then slows down with a constant deceleration to stop at the next set of lights after a total of 40 seconds. Find the distance between the lights. Well, to solve this, we do not know what the acceleration or deceleration are. So, draw a sketch graph with the information we do know. We know it accelerates at a constant rate, then continues at a constant speed for 25 seconds, and then decelerates. The total journey takes 40 seconds. Now we have a trapezium, and the distance covered is its area. Now we know the height of the trapezium is 16, the top of the trapezium is 25, and the base is 40. Now the area of a trapezium is a half the top plus the base times the height, which in this case is 25 plus 40 over 2 times 16, which works out to be 520. So the distance covered is 520 meters. Now you can treat the next 3 examples as an exercise. Pause the video at this point and try the following questions. When you think you've done them, you can restart the video and see the solutions. In question 1, we're told a car accelerates from rest with a constant acceleration until it reaches a velocity of 12 meters per second. It then maintains a constant velocity. After a total of 18 seconds, it's covered a distance of 168 meters. In part A, we're asked to sketch the velocity time graph of its journey and then work out how long was it accelerating for. Well, to start with, in part A, sketch the graph. We need to draw the car accelerating from 0 at a constant rate. After a certain amount of time, it stops accelerating and continues at a constant speed. Now we know it accelerates until it reaches a speed of 12 meters per second and then continues at a constant speed for a total time of 18 seconds. Let the time taken accelerating be t. Then the time that it continues at a constant speed is 18 minus t. And the distance covered is the area under the graph. So 168 is equal to the area of a triangle and a rectangle, which is a half times t times 12 plus 12 times 18 minus t. So that means 168 is equal to 6t plus 216 minus 12t, or 168 is equal to 216 minus 6t, or 6t is equal to 216 minus 168, which is 48, and so t is 8. So it was accelerating for 8 seconds. In question 2, we're told a car accelerates from rest with an acceleration of 1.2 meters per second squared. After t seconds, it continues at a constant velocity for a further time of 2t seconds. In part A, we're asked to draw a sketch graph of the journey. Now to draw the graph, we know that it accelerates from 0 at a constant rate, and then after time t, it continues at a constant speed. So the first part of the graph has width t, and the second part of the graph has width 2t. Now in part B, we're asked, if the total distance covered is 147 meters, find the value of t. If the acceleration is 1.2, then the height of the triangle is 1.2t. Well, the area of the trapezium is equal to the distance covered, which is 147. Now the area of a trapezium is half the top plus the base times the height. So a half into 2t plus 3t times 1.2t is equal to 147. This simplifies down to 3t squared is equal to 147, or t squared is equal to 49. So t is equal to 7. So our answer is t is equal to 7 seconds. Now in part C, we're asked to find the final velocity. Well, the final velocity is 1.2 times t, which is 1.2 times 7, or 8.4 meters per second, and so our final speed is 8.4 meters per second. In question 3, we have a particle has constant deceleration. After t seconds, it has a velocity of 36 meters per second and has covered a distance of 168 meters. It then comes to stop after a further 12 seconds. What is its initial speed, its deceleration, and the total distance covered? Well, to solve this, we first need to draw a sketch. So we can draw a straight line going down to the x-axis. Now, let the initial velocity be u meters per second. After t seconds, the velocity is 36 meters per second. The distance covered in the first section is 168 meters. So the area of the trapezium is 168. And it comes to a stop after a further 12 seconds. Now we know the area of the yellow section is 168. using the area of a trapezium is a half a plus b times h, we have a half into u plus 36 all times t is equal to 168. Or ut plus 36t is equal to 336. Now we can let that be equation 1. We now have two similar triangles, a blue triangle and a green triangle. So using the similar triangles, we have u minus 36 over t is equal to 36 over 12. In other words, u minus 36 is 3t, or u equals 36 plus 3t. Now we can let that be equation 2. If we substitute equation 2 into equation 1, we get 36 plus 3t times t plus 36t equals 336. So 36t plus 3t squared plus 36t equals 336, or 3t squared plus 72t minus 336 equals 0. We can divide all the way through by 3 to get t squared plus 24t minus 112 is equal to 0. And that does factorise as t plus 28 into t minus 4 equals 0. So t is equal to minus 28 or t is equal to 4. Now t must be a positive number, so t has to equal 4. Now if t equals 4, then u equals 36 plus 3 times 4, which is 48. So our initial speed is 48 meters per second. Now if we look at the green triangle, the acceleration is the gradient of the line. Now the line is sloping down, so the acceleration is negative, and it's minus the height over the base. So the acceleration is minus 36 over 12, which is minus 3, so the deceleration is 3. Now t is 4, and so the total time is 4 plus 12, which is 16 seconds. And the total distance covered is the area of the big triangle. So it's a half times the base times the height, which is a half times 16 times u, which is a half times 16 times 48, or 384. So the total distance is 384 meters.